The San Andreas Fault is one of the best examples of a strike-slip fault with frequent earthquakes. We have historical data for how destructive these earthquakes can be. For example, the 1906 and 1989 earthquakes in San Francisco caused a great deal of damage. Hollywood seems to have its own ideas for how the fault will behave in the future, like in the 2015 film San Andreas, but this is far from an accurate depiction. To understand earthquake behavior, we need to know about the rocks. But here's the problem. Earthquakes don't just happen right at the surface of the crust. They originate deep in the crust where we can't easily access. So what can we do? Enter SAFOD, or the San Andreas Fault Observatory at Depth. The SAFOD project took 12 years to develop, and it's the first scientific drilling project to cross the San Andreas Fault, retrieving rock samples from 3 kilometers or 10,000 feet. For context, the deepest mine is 4 kilometers depth, and the deepest borehole is over 12 kilometers, compared to the average continental crust thickness of about 30 kilometers. SAFOD targets an area of the fault that moves continuously throughout time, known as fault creep. Earthquakes occur to the south and north of the creeping section. The goal of SAFOD was to extract rock core from the fault zone. This is different from drilling for oil and gas because SAFOD is for scientific research and not resource extraction for profit. Drilling is the primary way scientists can access and analyze material at depth. The information we gain from these rocks contributes to our understanding of earthquake behavior. As earthquake geoscientists, we do all sorts of different tests and analyses on the entire core to understand how the physical and chemical rock properties change in relation to the fault zone. So what have we learned from the core, and how did we figure it out? First, let me introduce Emma.
Hi!
She will help answer those questions by explaining the rock types and analyses of the SAFOD core.
Here we have a cross-section view of the SAFOD drill path and the structures targeted during drilling. Here is the surface of the earth. This shows the borehole path. And here is the San Andreas Fault. On the Pacific side of the fault, there is crystalline bedrock, and on the North American side, there are sedimentary rocks. These two distinct units are separated by the Buzzard Canyon Fault and the 2 active strands of the San Andreas Fault. Throughout this video, we will talk about specific rock types and various analyses that were completed on SAFOD samples. Now let's go further in depth with these rocks. The first rock we encounter in the drill core is a granite, which is to the west of the San Andreas Fault. Granites are igneous rocks with a mineral composition of gray quartz, pink feldspar, and some darker hornblende. This sample is far from the fault zone, so it doesn't have obvious damage unlike other samples we will talk about. However, all of the samples in the SAFOD core have damage associated with faulting. Let's head to the rock lab to show you how we get our samples in the first place. As drill core is extracted from the borehole, it is placed in boxes like these. The full SAFOD core is stored in the Gulf Coast Repository in College Station, Texas. Requests are made through the Intercontinental Drilling Program to obtain samples for study. We had to request access to specific samples from the core, including this granite. We select rock samples from the core based on changes in lithology, interesting structures, and alteration features. The core is highly sought after by many other scientists around the world, and since this core was expensive to collect, there's a finite amount of rock material to work with. We have limited access to the samples, so we are pretty fortunate to work with all the samples we have. The next section we will investigate is the Buzzard Canyon Fault Zone, which marks the ancient boundary between the Pacific and North American plates. Fault motion has since shifted to the current main strands of the San Andreas Fault. We don't have a physical sample for the next section because drilling is complicated, especially near fault zones where rocks are damaged. Drilling and core retrieval is also very expensive, so we have to be selective about the rock samples we choose to extract. However, there are other downhole instruments that can rapidly collect rock property data about the subsurface. This borehole transducer travels down the hole and collects data such as temperature and resistivity. On the graphed transducer data, the x-axis is depth and the y-axis shows readings from porosity, resistivity, and gamma radiation. The peaks and valleys in these data help geologists differentiate between rock types, marked by different colors on the graphs. After the Buzzard Canyon fault zone, the next sample in the drill core is an Archos. An Archos is a type of sandstone dominantly composed of quartz and feldspar, which are two of the most common minerals on Earth. To get a closer look at the rocks and learn about their mineral composition, we make a thin section. A thin section is a slice of rock mounted to a glass microscope slide. To do this, we cut the core into small chunks called billets. First, we mark out where we want to make our thin section. Now Rachel's going to help us by cutting the rock. Hello. And here's the finished billet. From there, we send out the billets to a company that will epoxy the billet onto a glass slide and file it down to a thickness of 30 microns. When we receive the finished thin sections, we look at the sample under the microscope. We view the slide with different kinds of light filters, which tells us about the mineral composition and fine scale textures associated with fault slip and deformation. In this sample, we can see angular quartz grains that have cracks but are relatively undeformed. When we add a light filter, we can see that the matrix is fine-grained clay. After the Archos, we start to see rocks that have been more fractured, broken, brecciated, or sheared. In other words, rocks are increasingly deformed as we approach the San Andreas Fault Zone. We call this rock block-in matrix because it includes chunks of original broken rock into a background, or matrix, of very fine-grained material. This matrix has interesting microscale textures that we want to know more about. So let's head to the SEM lab. This is the SEM, or scanning electron microscope. The SEM scans the surface of an object at 30,000 times magnification using a focused beam of electrons. In order to use the SEM, you have to be a highly trained, qualified user. The samples that go into the machine, like this thin section, need to be kept really clean, so we use an air compressor and gloves. We load the sample into the machine, where we then use the monitors to focus and zoom in and out. After the electrons bounce off the sample and return to the detector, we see changes in the surface, rather than a color image, like through a regular optical microscope. In this sample, we can see the scaly fabric, which indicates fault movement. On this image, the fibers from the fault appear from right to left. Up next is the black fault rock. This rock may indicate that there was an earthquake at this location in the past. The fault is currently creeping, meaning there was a change in behavior. It is not unusual for a fault to switch from creeping behavior to earthquake behavior or vice versa. The minerals in this rock are so fine-grained we cannot identify features using only a microscope and thin section, as we did for previous samples. So we must use a different type of analysis called Raman. This is Dr. Kelly Bradbury. She's going to help us with the Raman spectroscopy.
This is the Raman spectrometer, which we use to measure fine-scale changes in molecular composition.
For this type of analysis, we can use either a thin section or a rock chip. We load the sample onto the mount and adjust the magnification to see fine-scale features. Lasers reflect off the sample and return to show Raman spectra, which appear as peaks on a graph. These spectra indicate imperfection in the crystal structure. A more perfect crystal structure indicates more recent rock heating associated with earthquake movement. Here we see slicken lines that indicate earthquake movement. At this point in the core, we have reached the part of the San Andreas Fault called the Southwest Deformation Zone, or SDZ. This is one of the two main locations where the fault is actively deforming. The SDZ is composed of a green mineral. We hypothesize that the mineral is serpentine. To confirm the mineralogy of this sample, we can use different geochemistry methods. One of those methods is called X-ray diffraction, or XRD. We powder the rock sample, then we prepare it for analysis by packing it into an aluminum sample plate. Then we feed the sample into this machine, and the sample is targeted by X-rays which reflect off each grain in the powder at a specific angle. The machine interprets the angles of the X-rays and reports them as spectra peaks, which are like fingerprints for each mineral and allows us to identify the types of minerals. These peaks indicate the presence of many minerals, including serpentine, the green mineral that we hypothesized. Serpentine is a slippery mineral and is related to talc. Talc is in baby powder and allows a baby's bottom to slide easily in a diaper and prevent it from chafing. Similarly, serpentine present in fault zones may allow the fault to slide past each other and creep. Adjacent to the SDZ is the CDZ, or Central Deformation Zone, which is the other strand of the San Andreas Fault that is actively moving right now. To determine what locations of the fault are actively moving, scientists place the caliper in the borehole. The caliper sits in the hole and records movement. When the fault moves, it is shown in the plot where the line strays from zero. The most motion is indicated by the biggest peaks and valleys. The data from the CDZ show that the San Andreas Fault is actively sliding at 4.8 millimeters per year. The final sample in the borehole is a siltstone. Though this bottom of the hole rock is not as close to the fault, it has still been deformed. For example, in this thin section, you can see some small displacements. Each of these sets of data helps us come to conclusions about the San Andreas Fault, such as past and present motions and geologic reasons for why the fault is slipping. Earthquake geoscience is a culmination of all sorts of analyses that help us identify trends and make interpretations.